In this video, we will discuss about the scales in the universe and the symmetry in physics. So let's start with the scales in the universe. Our everyday experience provides us with a sense of scale, the height of a person, the duration of a day, the weight of a bag of groceries. However, the physical universe operates across dimensions of length, time, mass, temperature, etc. that dwarf our familiar world, extending both infinitely large and infinitesimally small. So before we discuss the magnitude of the scale, let's quickly discuss about the different things that we find in the universe, from biggest to the smallest. So first thing is the multiverse. It is still a theory, but it is quite possible. So according to this theory, there is a multiverse which contains infinitely many universes. Then obviously our universe, it comprises of the observable universe. We will not be able to observe the part of the universe which is outside this certain distance range. So the observable universe consists of multiple galaxies, billions of galaxies. Then those galaxies consist of nebula. Nebulae are the star nurseries, where these are the dust clouds where stars are born. Then in nebula, as I said, there are stars. Then stars have some planets which orbit around them. It's not that only in our solar system there are planets. Almost all the stars, usual typical stars, have planets around them. And then planets may or may not have satellites around them. For example, our planet is Earth and the satellite is Moon. Then at the moment we do not know of any other planet, but we have living organisms on Earth. Then living organisms comprise of organs. Then organs are made up of tissues. Tissues are made up of cells. Cells are made up of molecules, and molecules are made up of atoms. Now in atoms, we have proton neutrons, and then these proton neutrons are made up of quarks. Apart from quarks, we have leptons. Leptons, for example, electron. Electron is a lepton. So we have quarks, we have leptons. Then there is a theory about strings. So according to this theory, all these subatomic particles, they are fundamentally made up of some strings. So different string vibrations give rise to different particles. Again, this is just a theory at the moment, but who knows, it might be true. Then these strings usually are at the Planck scale. Planck scale is the scale which we will discuss in this video as well. It is the smallest scale for mass, for time, for length. There is nothing which is smaller than this that we can physically understand with the laws of physics that we know of. So as you can see in this table, you have this various magnitudes of length, mass, time, energy and temperature. In this table, the units are meter for length, kilogram for mass, second for time, joule for energy and Kelvin for temperature. So I will not say all this, but you can see, you can take this screenshot and see what are these things made up of, or what are the magnitudes of all these things. So for example, the observable universe, the length of the observable universe is 10 to the power 27 meters. It's of the order of this. It's not exact, but I'm just telling you the order of the magnitude. Then its mass is 10 to the power 53 kg. Then the age of the universe is 10 to the power 17 seconds, and in billion years it is 13.8 billion years, or you can say 1380 crore years. Then during Big Bang, the energy output was 10 to the power 68 joules. And at the moment, the temperature of the space, or the cosmic microwave background, or whatever the energies which are present in the space, so the temperature is 2.7 Kelvin. Then similarly, we have our planet Earth. The diameter of Earth is in the range of 10 to the power 7 meters. Then the mass is 10 to the power 24 kgs. Then the age of Earth is, now if you see, there is this 10 to the power 17 in universe, Milky Way, sun and planets all. So you might be thinking, are all of them of the same age? No. So for example, the observable universe, or the universe, it is around 5 into 10 to the power 17 seconds old. Then Milky Way is around maybe 3 point something into 10 to the power 17 seconds old. Then Sun is around I think 1 point something 10 to the power 17 seconds. And similarly, Sun and planets, for example Earth. So our star Sun and our planet Earth, they are of similar age, almost similar age. So they are of different ages. So for example, in billion years you can observe, so 13.8 billion years, 13.6 billion years, 4.6 billion years, and 4.5 billion years. Then the energy required for this orbital motion of Earth is around 10 to the power 33 joules. Then the room temperature of Earth is around 300 Kelvin, or 27 degrees Celsius approximately. Now let's see some smaller things. For example, let's see a typical atom. So a typical atom has a size of 10 to the power minus 10 meter. Then the mass is around 10 to the power minus 27 kgs approximately. Then the time period of electrons orbital motion is around 10 to the power minus 16 seconds. The ionization energy, for example, to remove the electrons, what is the amount of energy required from the atom? It is around 10 to the power minus 18 to 10 to the power minus 17 joules. Then the concept of temperature does not exist for this atoms and protons, neutrons. Temperature is a bulk phenomena. So if there are multiple atoms or molecules, then only we can talk about temperatures in general. Okay. And then there is this electrons, which are very small, which are very lightweight. So again, you can see all the data. So the scales which are present in the universe are mind-boggling. There are things which are so huge, and then there are things which are so tiny. So this is again an interesting thing to contemplate about. So previously we used to think that atoms are the smallest, and we discovered electrons, protons, neutrons, and we thought these are fundamental. Then we discovered quarks. So who knows, what will happen after few years. At the moment we think we have a theory according to which the smallest things are strings, but again this is not yet proven, so who knows. And in this scale range also, we used to think that there is only our planet and this star and the planets revolving around Earth only in the geocentric model. But then we discovered that Sun is at the center, planet Earth revolves around it. So our perspective changed. So we used to think that only this solar system is there. Then we got to know that there are multiple galaxies as well. And now there are quite robust theories which suggest that there are multiple universes as well. So who knows, whenever we think that we have found the extreme, we find something new. So let's see what happens in the future. Now let me quickly discuss a few things about the Planck units or Planck scale. So as you can see in this, there are strings which have Planck scale like Planck length and then Planck energy, etc. So what is this Planck scale and Planck units? So in the late 19th century, physicist Max Planck realized that by combining fundamental constants of nature, for example, the speed of light c, the gravitational constant g, and the reduced Planck constant h cross. H cross means h by 2. H is the Planck's constant, and the value of h is around 10 to the power minus 34 joules in this magnitude. So according to him, one could derive units of length, time, and mass that were not based on arbitrary human conventions, but on the fabric of reality itself. So these units were called Planck units. So for example, what he meant is meter. Meter is the unit of length, but it is a human convention. This particular length was made by humans. So we selected some arbitrary length and we called it meters. So according to Max Planck, we can also derive the units for length, time, and mass if we combine the fundamental constants of nature. For example, c, g, and h cross. So let's see the different units. So for example, first is the Planck length. So Planck length can be obtained by square root of h cross g by c cube. And when you try to convert this into meters, this comes out to be 1.616 into 10 to the power minus 35 meters. This is an incredibly small length far smaller than even the nucleus or quarks. It is theorized to be the smallest possibly meaningful length. It is said to be the scale at which quantum effects of gravity become strong and our current understanding of space-time breaks down. Then there is Planck time, which is square root of h cross g by c to the power 5. And when we convert it into second, it comes out to be around 5.39 into 10 to the power minus 44 seconds. Again, this is the time it would take light to travel one Planck length. It represents the shortest possibly meaningful interval of time according to the current theories. Then there is Planck mass, which is square root of h cross c by g, which comes out to be around 2.2 into 10 to the power minus 8 kilograms or 22 micrograms. Interestingly, the Planck mass is not infinitesimally small, it's macroscopic, roughly the mass of a flea egg or a grain of dust. It represents the scale at which a particle's quantum wavelength, for example the Compton wavelength, would become comparable to its gravitational radius, which is the Schwarzschild radius, suggesting a regime where quantum gravity effects are dominant. It is vastly heavier than any known elementary particle. Planck units define the boundaries where our current separate theories of gravity, like general relativity and quantum mechanics, are expected to fail, and a unified theory of quantum gravity is needed. They represent the ultimate, most fundamental scales inherent in the universe, derived purely from its basic constants. So to conclude, the universe operates on scales that defy easy comprehension. For the near instantaneous flicker of quantum events, shorter than maybe 10 to the power minus 24 seconds, to the 13.8 billion year history of the cosmos, from the point-like nature of fundamental particles smaller than 10 to the power minus 18 meters to the staggering 10 to the power 27 meter expanse of the observable universe. From the nearly massless neutrino to the colossal mass of the galaxy clusters. Recognizing these scales is crucial for physics. It highlights the domains where different physical laws dominate. Quantum mechanics for very small, general relativity for very massive and large-scale structures, and classical mechanics for much of our everyday world. The existence of Planck scale hints at an even deeper layer of reality where these descriptions must ultimately merge. Studying these diverse scales reveals the extraordinary tapestry of the cosmos and our ongoing quest to understand its fundamental nature. Now let's discuss about symmetry and the laws of physics. So the universe in its intricate complexity frequently reveals underlying patterns and irregularities. From the mesmerizing spirals of a galaxy to the delicate structure of a snowflake, from the rhythmic pulse of music to the precise arrangement of molecules, symmetry manifests in myriad forms. Beyond aesthetical appeal, symmetry plays a profound and fundamental role in the realm of physics. At its core, symmetry in physics signifies an immunity to change. A system or a physical law possesses symmetry if it remains invariant or appears the same after undergoing a specific operation or transformation. This concept can be understood in various ways. So, for example, invariance under operation. So, a thing is symmetrical if it can be subjected to a specific operation. For example, rotation, translation, reflection, and it appears identical after that operation. For example, a square exhibits rotational symmetry because it looks the same after rotations of 90 degree, 180 degree, 270 degree, 360 degree, and so on. And one more thing, the rotation is to be around its center. Then we can also understand in this way immunity to change. It implies that certain characteristics or behaviors of a system are unaffected by particular alterations to its state or environment. Then we can also think of it as the expression of equivalence. Symmetry represents an equivalence between different states or configuration of a system or between different perspectives from which a phenomena is observed. So in the context of physical laws, symmetry means that if we perform certain operations, the result predicted or observed by these laws remain consistent. This profound principle ensures the universality and the predictability of physics, allowing us to formulate laws that are not dependent on arbitrary factors like location, orientation, or time. So now let's discuss about the categories of symmetry. Symmetry in physics can be broadly categorized based on the nature of the transformations involved and their spatial or temporal applicability. So first, Let's see the category based on continuous and discrete symmetries. So the distinction between continuous and discrete symmetries lies in whether the transformation can be performed incrementally or only in distinct steps. So first let's understand continuous symmetries. These are the operations that allow a system to transition from one state to another through an infinite continuous set of transformations. Imagine rotating an object. You can rotate it by any infinitesimal angle. A group whose elements can be reached by continuous change of one or more parameters such as an angle or a position is called a continuous group or a Lie group. Let's see some examples. So first is like a smooth dial. Imagine you have a volume knob on a radio. You can turn that knob a tiny bit or a little more or a lot. You can stop it at any point in between. It's smooth continuous movement. So this is an example of continuous movement. Then real numbers under addition. Think of a number line. You can start at 0 and move a little bit in positive direction or in negative direction. For example, you can go up to 0.1 or 0.2 or 0.001. So you can go by any small amount. So for example, if you add things, you can add any small amount. If you subtract things, you can subtract any small amount. So again, this is continuous. Next example is rotation in space. So imagine spinning a globe. You can spin it a little bit, then a tiny more, then little bit more. These are endless small turns you can make. So this is again continuous. Then let's see some physics examples. So for example, Lorentz transformation in physics. So this is like how you view time and space change smoothly as you speed up or slow down. There's no sudden jump from one speed to another. You pass through all the speeds in between. So this is an example of Lorentz transformation. So again, all these are examples of continuous symmetries which are changing continuously. Then there are discrete symmetries. Unlike continuous transformations, discrete symmetries involve operations that cannot be achieved through continuous changes. These are all or nothing transformations. If the elements of the group can only be labeled by integral indices, it is called a discrete group. For example, like a light switch. Imagine a light switch. It's either on or off. There is no halfway on or a little bit on. It's a sudden distinct change. Another example is parity identity pair of rotations. Think of looking in a mirror. So that means you are either looking at yourself, which is the identity, or your reflection, which is the parity, a flipped version. So there is no in between state. It's either you or your image. There is nothing in between. Then next is even integers under addition. So imagine you have only even numbers. If you are only talking about even numbers, 2, 4, 6, 8, etc. If you add any two even numbers, you always get another even number. For example, 2 plus 4 is 6, 4 plus 8 is 12, and so on. So you can't get an odd number by adding even numbers. You jump from one even number to the next. So these all are discrete examples. So these are discrete symmetry examples. Now there is another way to classify symmetry, which is global symmetry versus local symmetry. So what is a global symmetry? This occurs when a mathematical operation leaves a system unchanged and applies uniformly across all space and time. The transformation parameter is constant everywhere. So for example, like moving or turning a whole painting. Imagine you have a painting on your wall. Now there are two cases. One is global spatial rotation and another is global spatial translation. So first, global spatial rotation. So if you physically rotate the entire painting on the wall, every single part of the painting rotates by the exact same amount. The top moves on this side, the bottom moves on the other side, but the whole thing turns uniformly. You don't rotate just one corner, you rotate the whole thing. This is global spatial rotation, because whole thing is rotating. Then there is global spatial translation. So if you pick the entire painting and move it at a different wall, all the parts of the painting moves by the exact same distance in the same direction. The top left corner moves 5 feet to the right, so does the bottom right corner and every point in between. So in both these cases, this is a global change. Whole thing is changing. Now let's discuss about local symmetries. In contrast, local symmetries refer to operations where the transformation depends on the specific location or moments in space-time. The transformation parameter can vary from point to point. These are often associated with fundamental forces in nature, leading to the concept of gauge theories. So, for example, like wrinkling a blanket or stretching Play-Doh. So, imagine you have a large blanket spread out on the floor or a big piece of Play-Doh. So you can do multiple things. For example, wrinkling a blanket. You can grab one part of the blanket and pull it up, creating a wrinkle just in that spot. Okay, only that spot. Another part of the blanket might stay flat, or you might create another wrinkle somewhere else. So this transformation, this wrinkling of the blanket is local. It is only where in a small region, small portion. Then another example can be stretching the Play-Doh. So you can pull and stretch the Play-Doh in one area, one location, making it thinner there and making it thicker somewhere else. Or you can let it be untouched at some places. So the expansion or stretching happens differently at different points. Again, this is local. This is specific to certain location. So in this examples, the change or transformation is not uniform. It happens differently or more intensely or only at specific points rather than affecting the entire system in the exact same way. So this varying change from point to point is what makes it a local symmetry. So now let's discuss about specific types of symmetry operations in physics. So there are multiple symmetry operations, for example translation, rotation and so on. So let's discuss them one by one. So let's start with the translational symmetries of space and time. So let's first start with spatial translational symmetry. So if you conduct an experiment, its outcome should not depend on where in the universe you perform it. If an experimental setup is relocated to a different place, the system will behave identical to how it did in the original location. This might seem intuitive to you, but it is a profound observation. Had the outcomes differed with location, we would need different physical laws for different places. So what I mean is that one location of your house, the laws of physics would be different, and another location of your house, the laws of physics would be different. It would be so complicated. Fortunately, the results are consistent across different locations, demonstrating spatial translational symmetry. This means physical laws are uniform across space, and any reference point can be used without affecting the fundamental interactions. Now next is the temporal translational symmetry. So similar to the space, if we analyze a system at any point in time and find consistent behavior, this demonstrates temporal translational symmetry, indicating that physical laws are also uniform over time. And what we know is that this is true. The results of an experiment does not depend on when the experiment is performed in general. Next is the inversion symmetry or point symmetry. So inversion symmetry or point symmetry implies that an object or system is unchanged when all its spatial coordinates are inverted relative to a central point, often called the origin. So let's see how inversion symmetry works. Imagine a central point in a system, commonly considered the origin. Let's call it 0, 0, 0 in the coordinate system. Then if you take any point in this system, say x, y, z, inversion symmetry means there is a corresponding point at -x, -y and -z. The system looks the same when viewed from this inverted perspective as it does from the original. So essentially, if you were to perform a 180-degree rotation around this central point and then translate the object through the central point, the object or system would appear unchanged. So let's see some examples. In molecular chemistry, we have this molecule of methane, CH4, which exhibits inversion symmetry. Its central carbon atom is symmetrically arranged with 4 hydrogen atoms in 3 dimensions. If you pick any hydrogen atom and draw a line through the carbon atom to the opposite side, you will find another hydrogen atom at an equal distance but in the opposite direction. Now let's see example of a mathematical sort. So a circle has inversion symmetry about its center. Reflecting any point on the circle through its center yields another point on the circle. Now let's discuss rotational symmetry or line symmetry. It means that the physical description of a system remains invariant under rotations about an axis. So let me clarify. The previous one was about a point. Okay. Now this one is about a line. So this is the difference between these two. So now let's see some examples. Let's see, okay, Earth's rotation and physical laws. So the Earth's rotation on its axis does not alter the fundamental laws of physics. These laws are invariant no matter the orientation or rotation of the system. Then falling objects. Consider a man falling from a building, oriented in any direction, up or down, left or right. Regardless of how we rotate him during the fall, the outcomes dictated by the laws of physics, particularly Newton's laws, remain consistent. This demonstrates rotational symmetry. The laws remain consistent. The laws of physics do not change even if we alter the system's orientation. Another example is in mechanical devices. While most mechanical devices function the same way regardless of their orientation due to rotational symmetry, a grandfather clock is an exception. If tilted, its pendulum might obstruct against the case, ceasing its function. This illustrates that while the internal mechanisms are subject to the same physical laws, their effective operations can be influenced by the orientation due to the external gravitational forces. This illustrates that while the internal mechanisms are subject to the same physical laws, their effective operation can be influenced by orientation due to external gravitational forces. This example highlights that while the laws themselves are constant, their manifestations can vary with the system's orientation relative to external forces, for example, gravity here. Next is the time reversal symmetry or T-symmetry. Time reversal symmetry refers to a theoretical property where the fundamental laws governing the behavior of particles and fields appear identical whether time moves forward or backward. So for example, for a process to exhibit time reversal symmetry, if it were recorded and played in reverse, the particles would appear to behave in a manner consistent with the same physical laws as they did when viewed in the original forward direction. For example, a collision between two particles that come together and then part ways, when played in reverse, would show the particles behave according to the same laws. So what are the applications of this certain symmetry? So in quantum mechanics, we have many equations. For example, Schrödinger equation, which are time reversal invariant. This means that if a quantum state evolves one way in time, it can theoretically evolve in this exact reverse manner if time flows backward. Another example is in electrodynamics. In electrodynamics, Maxwell's equations describe the electric and magnetic fields. They are also symmetric under time reversal, implying that electromagnetic phenomena could theoretically operate the same way if time were reversed. Now, there are certain cases where this time reversal symmetry is broken. So, while many microscopic processes exhibit time reversal symmetry, there are notable exceptions, particularly in complex systems or involving specific fundamental forces. For example, in thermodynamics, the second law of thermodynamics states that entropy in an isolated system always increases over time. This is a fundamental principle where time reversal symmetry does not hold. If time were reversed, entropy would decrease, contradicting this law. This introduces a directionality to time, often called the arrow of time, which distinguishes the past from the future. Another example is in weak nuclear forces. In particle physics, specific interactions involving the weak nuclear force, which is responsible for radioactive decay and hydrogen fusion in stars, violate time reversal symmetry. This was experimentally confirmed through observations of specific decay processes that do not look the same when time is reversed. This concept deepens our understanding of physical laws and highlights the complexities and nuances inherent in the study of time and its properties. Next is the reflection symmetry, which is also called parity, mirror, line, handedness symmetry. Reflection symmetry involves transformations where objects do not remain invariant but transform into their mirrored counterparts. This property is intimately linked with the concept of handedness or chirality. So what is handedness or chirality? So an object or a system is chiral if it is distinguishable from its mirror image. That is, it cannot be superimposed onto it, just like human hands, where the left hand is a non-superimposable mirror image of the right hand. Chiral objects have distinct left hand and right hand version. For example, most screws are right-handed, moving forward when turned in the direction to the right hand's curling fingers. So if you see this in the mirror, this direction appears left-handed, but the functionality remains the same because in the mirror also the screw will be going in. demonstrating that physical laws accommodate both orientations without violation. On a molecular level, handedness is represented by reflection symmetries where molecules exist in mirror image forms known as stereoisomers. Example, dextro and levo forms of sugar. Water remains the same upon reflection, whereas the other molecules transform into their mirror images. This molecular asymmetry plays a crucial role in biology also. Another thing that we need to understand in reflection symmetry is the parity symmetry or P symmetry. Parity symmetry is a type of discrete symmetry which involves an all or nothing reflection. There are no partial reflections in physics. Essentially, if parity is preserved, the laws governing physical phenomena should appear identical whether observed directly or through a mirror. This implies that dynamical physical processes and fundamental physical objects should behave the same in the mirrored environment as they do in our normal environment. For example, the principles governing electrodynamics and gravity should be consistent in both the mirror world and the real world. Now, what is the historical context of this? Historically, investigations using particle accelerators showed that at the most basic level, physical processes did not reveal any differences between their original and mirrored versions. Up until the 1950s, this observation led many to believe in perfect parity symmetry in nature. In quantum mechanics, parity involves flipping the sign of all spatial coordinates, like viewing an object in a mirror. Mathematically, if the physical description of a system is invariant under this coordinate inversion, the system is said to have parity symmetry. In quantum field theory, this translates to asking if physical processes involving subatomic particles are conducted in a mirror reverse situation, would the physical laws still apply in the same way? Now, there is a violation to this parity. Weak nuclear force responsible for the processes like beta decay and hydrogen fusion in stars famously violates parity symmetry. This was first experimentally confirmed in the 1950s by Chen Xiongwu, who conducted experiments involving the decay of cobalt-60 nuclei, which contradicted the then prevailing notion that physical laws are symmetric under parity inversion. This discovery showed that the weak force inhibits a preference for handedness in its interactions, meaning it can distinguish between a process and its mirror image, leading to maximally parity violating processes. In essence, while gravity, electromagnetism and strong nuclear forces exhibit parity symmetry, that means the laws governing these forces behave the same way in a mirror reverse scenario, the weak force does not. Now, what are the implications of this? The violation of parity in weak force has deep implications. It introduces a fundamental asymmetry at the smallest scales of nature, which has consequences for theories explaining matter-antimatter asymmetries and the conditions in the early universe. So what is this matter-antimatter asymmetry? So we do not know how this universe came to be. There is this theory which suggests that there was slightly more matter than antimatter in the beginning, and which resulted into the formation of our universe. So this asymmetry can be understood with parity violation. This asymmetry is also a critical factor in the development of theories beyond the standard model of particle physics, as it indicates that our universe does not behave identical when mirrored, pointing to an intrinsic directional bias at the most fundamental level. Now, there are other important symmetries as well, which we will just tell you about in short. So there is charge symmetry, which says about invariance of physical laws under transformation of particles to their corresponding antiparticles, for example electron to a positron. And then there is this helicity symmetry, which is the invariance related to the spin direction relative to the direction of motion of particles. As noted with neutrinos, this can be broken for certain particles by weak force. Then there is symmetry under uniform velocity, like Galilean invariance or Laurent invariance. So invariance of physical laws under transformations to a constant relative velocity. So in this, Galilean invariance applies to classical mechanics, while Lorentz invariance applies to electromagnetism and relativistic mechanics, forming the cornerstone of special relativity. Then there is symmetry under interchange of identical particles. The laws of physics remain unchanged if two identical particles, for example 2 electrons, 2 protons, 2 photons, are swapped. This leads to profound consequences in quantum mechanics, determining whether particles are bosons or fermions. So let me tell you in short about broken symmetries. So the weak force breaks time reversal symmetry, parity symmetry and charge symmetry. and it also violates CP symmetry together, that is charge parity symmetry together as well. But CPT symmetry is not violated, that is charge parity and time reversal symmetry altogether. This is not violated. This preserves the conservation of probability. Now we have come to the most interesting part of this chapter, symmetry and the conservation laws. One of the most profound and elegant connections in physics is the direct relationship between symmetry and conservation laws. This fundamental insight was first articulated by the brilliant mathematician Noether in 1918. So before we move to the Noether's theorem, let's discuss a couple of things. One is conservation. In physics, a quantity is said to be conserved if its initial value within a closed system is equal to its final value after some process or interaction. Conservation laws are cornerstone of physics, enabling us to predict and understand the behavior of systems without needing to track every intricate detail. One more crucial thing is that this Noether's theorem, which we will see, applies specifically to the continuous symmetries, not discrete symmetries. While discrete symmetries are important for understanding the structure of physical laws, as seen by the parity violation, they do not by themselves lead to conserved quantities in the same direct manner as continuous symmetries. Okay, so now let's see what is Noether's theorem. So Noether's theorem states that for every continuous symmetry of the laws of physics, there must exist a conservation law, and for every conservation law, there must exist a continuous symmetry. Now let's see the examples of this. So you can see this table. So in this table we have the symmetry type, and then we have the conservation law associated with it with some example. So one is the time translation invariance. So according to this, the laws of physics don't change over time. So this gives rise to the conservation of energy. Then there is this special translational invariance. This states that the laws of physics don't change based on your location, and this gives rise to conservation of linear momentum. Then there is special rotation invariance. It states that the laws of physics don't change if you change your orientation in space. This gives rise to conservation of angular momentum. Then there is boost invariance. This states that the laws of physics are the same for the observers moving at a constant speed relative to each other, and this gives rise to conservation of center of mass of motion. Then there is gauge invariance or U1 electromagnetic symmetry. This states that a recalibration of an abstract property like phase doesn't change physics. This gives rise to conservation of electric charge. Then there is SU2, SU3 symmetries, which gives rise to conservation of isospin and conservation of color charge. Again, this might be new to you, so you need not worry about this. You will understand these things better when we go to this particular things in detail in later part of the book. And then there are discrete symmetries. They do not have any direct conservation law associated with them, but let's see them quickly as well. So there is parity, which states that the laws of physics are the same if you reflect everything in a mirror. Then there is charge conjugation, which states that the laws of physics are the same if you replace all particles with antiparticles. Then there is time reversal symmetry, which states that the laws of physics are the same if you play a process backward in time. And then there is CPT symmetry, which is combined charge, parity and time symmetry, which states that the laws of physics are the same if you combine all these three: charge, parity and time symmetries. So interestingly, as we saw earlier, the weak nuclear force violates parity as well as it violates the charge conjugation. But when we see this CPT symmetry, all of this combined, then these are always conserved. Weak force also follows this. So this implies that the particle antiparticles have the exact same mass and the lifetime. So to conclude, this remarkable theorem underpins much of modern physics. It explains why fundamental quantities like energy, momentum, angular momentum are conserved, directly linking these conservation laws to the inherent symmetries of the space and time. It provides a powerful framework for understanding the universe, demonstrating that its enduring regularities are a direct consequence of its underlying symmetries. The study of symmetry, therefore, is not merely an intellectual exercise but a fundamental pathway to uncovering the deepest principles governing the physical reality.